dRAID, finally, well, almost finally. So I'm going to talk about dRAID and where we are with it, and give you an idea of when you're actually going to see dRAID here soon, and why it isn't really here. We were hoping for 2.0, but we didn't quite make it. So the history here, again, this is a feature that was originally developed at Intel by Isaac Wang. He gave talks on this at the OpenZFS Summit in 2015, 2016, 2017. It kind of languished for a little while, and then was rebased by Don Brady around the time he was doing allocation classes. The feature was picked up by Cray in 2018 because they wanted to use it as a key capability in a ZFS version of its distributed storage product. Brian Belledorf adopted the Cray version of the feature in early 2020. He created what is the current PR for the feature now. And he and I have been working on this now for a number of months, trying to get all the pieces pulled together and get this integrated. I don't. I get, there it is. Sorry. All right. So I want to introduce a little bit of terminology before I start in, mostly because there's a lot of confusing terminology here, and that can easily get conflated between RAID and dRAID. So I want to talk about group size. Group size is the number of pieces that, or number of columns that data is partitioned into plus parity. So, you know, obviously the number of data columns sort of defines how much overhead your redundancy is going to cost, and the amount of parity determines how much redundancy you have. dRAID size then is the number of drives that are actually used for storing data within a dRAID configuration. It does not include the spare drives. So when I talk about dRAID size, I'm talking just in the data drives or the data drive capacity. A dRAID row is a 16 megabyte chunk of space allocated the same offset across all the drives in the dRAID configuration. And for example, row 0 is offset 0 through offset 16 meg across all drives in the config. And you'll see why that's important here in a little bit. And a permutation slice is one or more rows which are permuted based off of the dRAID permutation array. And the actual number of rows is derived, per slice is derived from the least common multiple of the group size and the dRAID size. So keeping all that in mind, what is dRAID? So dRAID is RAID, in our case, in ZFS's case, is RAID Z declustered. So what that means is on the left, you see here an example of what a RAID Z layout might look like, where you have two RAID Z top levels with a hot spare allocated for your pool. And the equivalent or the contrast of that as a dRAID would be to say, all right, I want a dRAID defined with a group size of 5 across these 11 drives, with one of the drives being drives with a spare capacity. So in the left, or in both sides, you see that I've divided the tables into rows, and these rows are what represent both in this case, both a group, a permutation slice, and a dRAID row. All right, so each row is permuted from a traditional layout across drives on the left in RAID Z to a semi-random layout on the right based off of a computed permutation that allows us to get relatively random layout of our data across the entire pool. So why is that important? I'm really slow in advancing on this for some reason. Okay, so let's talk a little bit more detail about RAID-Z versus dRAID. First of all, the dRAID implementation is actually layered on the RAID-Z code. It uses a different map allocation function, but its pipeline, its functions are almost identical to the RAID-Z code, and actually calls into the RAID-Z layers to do its I/O. The RAID-Z layout, in a RAID-Z layout, each group is constructed from a set of physical drives, and the columns of that extend the entire length of the drive. So the only constraint you have is that allocations into those RAID-Z groups must be a multiple of parity plus 1. This is to prevent stranded space, which is so small that you can't actually allocate from. So anything that's smaller than parity plus 1 is not allocatable in a RAID-Z layout. So for example, a 1K data requires 2K of space with a single parity. dRAID layout, on the other hand, groups are divided into rows of 16 meg. So rather than consuming the entire disk in a column, each column is chunked in 16 meg pieces where contiguous 16 meg chunks don't necessarily reside on the same drive. This is the permutation. So group rows are non-contiguous on physical drives. And here allocations must be a multiple of parity plus data. So not just parity plus 1, but parity plus data. That means that for the same example, a 1K data is going to require 2.5K of space in a 5-disk group size group. And if the group was larger, it was an 8-disk group, you'd have to have another 3 records, 3 512 chunks in that allocation in order to align it appropriately to the dRAID constraints. And I'll talk why that is here in a minute. So why decluster? There's a couple of very good reasons. One, spare drives are leveraged here. So in the example I showed before, the first example, we had our hot spare. That hot spare is a spindle that sits idle most of the time until there's actually a problem that needs to be utilized. It's never used except to be ready to go. In a declustered configuration, we distribute the spare capacity throughout the dRAID, so the actual spindle is leveraged with a combination of data and spare capacity, and every spindle is the same that way. Each group's data is randomly distributed across all the drives. This decouples the redundancy group from the number of data drives so that as we are allocated reading and writing, we can consume from all of the spindles rather than just a set of spindles which make up that particular group. So the data reconstruction can leverage all the drives. Reads are shared evenly across all the drives. Writes go to spare blocks, which are distributed across all the drives. This allows us to use all the spindles all the time. And most importantly, sequential resolver works in this configuration. And that is because of that constraint of all rows must be full rows, i.e. we always have minimum allocations of parity plus the data, so we always fill the entire row. This way we can construct our pseudo blocks for the dRAID because we know exactly where the parity is going to be laid out and where the data is. So how do you go about creating a dRAID in ZFS? We had a new top-level device type. It's called a dRAID, very similar to a RAID-Z. We support dRAID 1, 2, and 3 for the various parities. You can specify at creation a redundancy group size. So the :5D example here, dRAID 1:5D would be a group size of 6, 5 data, 1 parity. The default for the group size, for the data portion of the group size is 8. In general, though, the group size has to be less than the number of data drives in dRAID config. Now, this may not seem obvious, but if you had, for example, 3 drives and tried to define a group size of 4 on that, it doesn't work because you don't have enough drives to actually provide the level of redundancy that you're asking for. You only have 3 drives. You can't get 4 drives worth of redundancy. But you can define smaller than, any number smaller than the group size. Than the dRAID size. You can specify the spare capacity as a drive count. So in this example, dRAID 1:5D:2S says I want 2 drives worth of spare space. So that means that we will take out of the total specified drives for the dRAID config, we'll reserve 2 of those as sort of spare space worth of drive capacity. We now expose, or in the status, as many as we can of the actual configuration. So because the groups are now sort of pseudo groups within the config, there's no easy way to say, all right, these 4 drives belong to this group and these 4 drives belong to this group, as you would see in a RAID Z. Instead, it's random, so we present it as a top level dRAID and all the drives, but in the dRAID name, we tell you how it's been partitioned up logically. And at the end, we have our spares, and notice these are pseudo spares, again, because we haven't reserved physically 2 drives, we have reserved 2 drives worth of space, and these 2 represent the pseudo handles to access that drive space. It's been distributed across all the drives. All right, so I want to move on now to talk about sort of the various issues that we ran into that Brian and I had to address as we were trying to get this code ready for integration. Everything I've talked about to date was pretty much there in the bits when we took over the bits for integration. One of the things we had to deal with was the permutation array. In the implementation, in general, you have to have a permutation array that defines the permutation for each slice of the config of the dRAID configuration. And that had been generated at pool creation and stored in the label. And it was critical information that had to be present when you first load the pool, because all data all access to the pool has to go through, figuring out the permutation, and was put in every label because it was critical data that if you lost that data, you could not access any data in the pool anymore. You didn't know how to reconstruct the chunks of groups and slices, and if you lost the permutation, you know how to fit all that data back together again. So there were sort of 2 issues there. One was the fact that we were using up a lot of label space for this, and 2 was the fact that if we lost it, that's really, really bad. So the answer we came up with was to predefine essentially the permutations for a configuration. Brian figured out essentially a means of coming up with a predefined set of permutations, or at least of a seed for calculating permutations that would always produce the same permutation and would be a relatively optimal permutation. And so that is how it's now handled inside of the dRAID code. There's a table of the permutation seeds that are used to generate permutation on the fly as soon as you bring it up. There's no risk of losing the permutation as part of the implementation. It's of course instantaneous, basically, because it's all there to start with. You're not going through a computation phase of figuring out what your permutation array is going to look like. And there's no need to store it in labels anymore, so we've freed back up this space that we've been consuming in the labels. All right. Second issue that we addressed was some group size constraints. So in the original implementation, there was this notion that the dRAID slice was always equivalent to the dRAID row. So you only ever had one row in your slice. Basically, that meant that you had to divide your groups evenly into your number of drives in the dRAID. So your drives, your dRAID size. If you wanted even group sizes, that meant that for example, a 30 drive configuration, you could only support either 3 drive group, 5 drive group, and 10 drive group, or 15 drive group, because it had to be an even multiple. You couldn't, for example, support in this configuration with 30 drives an 8 drive group because it didn't divide evenly. We did work out a variation or enhancement to dRAID, which allowed you to define a configuration which used different size groups to fill out the set of groups that went into the row. This allowed us more flexibility and allowed us to define group sizes that were made more close to what you were looking for as a consumer, as a user of this capability. The problem was that it was not optimal, obviously, and you'd end up with these sort of some groups for one size, some groups for another size, and it's hard to reason about a pool when you have different sized groups like that, in terms of performance at least. The better answer was to introduce this notion of tiling. So instead of requiring that each slice have just a single row in it, we say, well, the number of rows in the slice is actually going to be the least common multiple of the size of the group and the size of the dRAID. And this allows us to tile in as many groups so that we get an even multiple and will evenly fill up the space in a particular permutation slice. That decouples basically the group size from worrying about the number of groups. So in earlier iterations of dRAID, you had to specify not just group size, but number of groups. Now you never specify number of groups, you only specify your group size, and the number of groups is generated for you automatically based off of this math. The next issue, which we had to address, was stranded space. I mentioned already that a block allocation has to fit, is padded out to each to the full group width, but an additional constraint was that the allocation had to fit into a single group row. That means that your group was, for each group row, you have a chunk basically of 16 megabytes, but the next row is not necessarily on the same drive. So as you're allocating into it, you actually have a different set of blocks, a different set of drives, which represent the next row in that group. This did not work well with the logic in RAID-Z, because that's not ever an issue with RAID-Z. RAID-Z, you always have the entire drive space to deal with in the columns. You never had to switch drives in the middle of a group, or sorry, of the middle of a block. What that meant, though, for dRAID, because we had this constraint, was that you get in a situation where you can fill up a group with the 16 meg chunk and get to a point where, all right, I'm trying to allocate this block and there's not enough space. And so I'm going to move over to another group to allocate it and want to have more space in it. And you can end up with bits of space at the end of groups which are not easily allocated. All right, so if you end up stranding the space. Now, in theory, you could eventually use that space with smaller block allocations, but it was an awkward model where you could end up with, particularly in environments where you're doing a lot of large block allocations, which is what is typical in a dRAID configuration, where you have a lot of sort of these small chunks of space, which you're never going to really make use of. And given that there are a large number of rows in a large configuration with multiple drives and large drives, that could be a problem. So the answer we came up with here was to leverage the multi-row allocation maps that were developed for the RAID-Z expansion project. Thank you very much, Matt. That allows us to actually define a block pointer or block allocation unit that can span two separate groups. So the first row will say these columns reside on these set of drives, and the second row says, and the rest of these columns reside on this other set of drives. So now we can split a block across two groups, and so we can pack information and not have to worry about this problem. So this constraint goes away. Next, and finally, we had to deal with the issue of space inflation. This is a problem that is similar to the RAID-Z problem, where we have to allocate additional blocks to fill out the constraint for the actual allocation size, so parity +1 in case of RAID-Z. But it gets worse with dRAID because we're doing entire rows, or entire group rows anyway. And so we now are potentially allocating or filling a number of sectors that are not part of the data itself. So this could be particularly significant if you're writing a lot of small block data. Let's go back to our example of, let's say we have a 8 wide stripe with, say, 2 parity. So we have 3K, and this is a 512 sector size. So we have 3K of space, then is our sort of minimum allocation size. So if you have any allocations, you start saving blocks that are small in 3K, you are going to consume 3K of data space for those blocks regardless. So the minimum allocation size, as the stripe width gets bigger, the minimum allocation size gets bigger. And this is even worse if you're looking at a 4K allocation sector size. Suddenly there's a significant amount of space potentially being left on the table to fill out these rows. What's also important to realize here is that in dRAID, we explicitly zero fill these extra sectors. So when we write them, we actually have to write out zero filled rights to fill these sectors. That's important from the sequential resolver perspective, because we need to be able to evaluate parity from arbitrary rows where we don't know where the data is and where the fill blocks are. The zero filled data is critical to us. So the answer here, there is, it's not a perfect answer. Allocation classes go a long way towards helping here. So you can simply define some allocation classes, some additional capacity in your pool, and say, all right, small block data, metadata should be written out to these drives, which are configured in a more optimal configuration for smaller block data. the other is to use large blocks, right? dRAID is definitely tailored in certain ways for large block data. It wants the larger the block, the less overhead you're going to see with this kind of fill inflation. Percentage-wise per block, it'll be very small. So we at Cray tend to write 1 meg, 2 meg, up to 16 meg. We usually use the large blocks all the time, and so even if our blocks don't fit evenly, aren't divided evenly into our group width, the overheads are minimal for us, and so that helps. But you're always going to have to be aware of these overheads. You're going to end up seeing situations where you may see your space being used up faster than you realize it. So we're not stranding any space here, but we are inflating your allocation sizes. And so the way that manifests is going to be that it seems like my pool fills up much faster than I anticipated it because I wrote out a whole bunch of small files. All right. So what about drive replacement performance? Again, one of the main focuses of dRAID was all about figuring out how to improve our device replacement and device rebuild process. And so with a dRAID configuration using sequential resilver, the time it takes to do a device replacement is significantly faster than the time it takes to do it where you're using a single distributed spare. The spare capacity is, again, using all the drives, and so we're reading from all drives to pull in the data necessary, reconstructing using data from all drives simultaneously, writing across all the drives to fill in the hot spare data. For small groups, so in a large configurations, in this example here, we have 90 drives with if you have a lot of small groups, you're going to see some amazing performance. As you see here, we're getting a 10x faster replacement versus even with a relatively large group size here, 15 blocks, 15 wide stripes, you're seeing still significantly faster rebuild rates. And that's just a win. And that's the most important feature, I think, for dRAID. It is important to notice that, it does improve even when you're doing wide stripe. It's still a big boost. We have examples in Cray where we actually use, a dRAID configuration with just a single group in it, and it still gives us benefit because of the fact that, one, we've gained the spare as this extra spindle in the config, and two, even though the reads are not any faster, as we're still able to read across all the drives, the writes are happening faster because we're actually writing to all the drives for the spare space. And that tends to be a limiter in device reconstruction. All right, so when is dRAID going to be available? As I mentioned, we originally targeted ZFS 2.0 release. Brian and I worked really hard to make it into that release, and I twisted his arm hard when it got down to late August, and he wanted to cut the 2.0 release, but it just wasn't quite there. We still hadn't finished all of the issues that I've just covered. And there was, a bit of work to harden and fix up various issues that showed up in the code as we were doing our work. So we end up getting pushed out of the 2.0 release, and we're now targeting the 2.01 release. So I think we're doing well for that. Current status of the pull request is that it's converging. I think Brian said that he has almost everything that he wants in there in terms of issues, addressing all the issues he's seen with ZTS and D-loop issues that he's encountered while doing a lot of testing. So I think it's pretty hardened from that perspective. We have been doing a bunch of testing at HP Cray to hammer it with our workloads, and it looks very solid. At this point, I think we're largely waiting on final code reviews for the release. So fingers crossed in the next few weeks, perhaps, or at least by end of year, we'll have that in, and the 2.1 release out late this year, early next year timeframe. Brian can correct me if he decided otherwise. So what are the next steps? Obviously, we need to get this thing integrated. I said there was a couple of small issues that are being closed up and getting the final code reviews done, but it's almost there. And the next thing we're kind of looking at, or one idea we're kind of looking at beyond, is dRAID expansion. So the idea is that could you add a drive to a dRAID configuration? And I think the answer may be yes. So I think this could be an interesting thing to look at. So if anybody's interested in thinking about that, maybe working on some prototype code, let's get together at the Codeathon and see what we can do. All right, with that, we can move back to Q&A.
All right, so yeah, we have about 6 questions now. So there is a few from Jan. First one, what makes a permutation bad or optimal for dRAID?
So the whole idea with permutations is to derive a set of laying out the data such that you get as one, you randomly distribute your data across all your drives so that as you do your I/O, you're hitting as many drives as possible all the time. And you have to also in such a way, of course, that you don't have any overlaps that would destroy your redundancy. So if you lose a drive, you can't actually. You have to be able to preserve the data if you have parity. So if you have single parity, you should be able to lose a drive and not have a problem. If you have dual parity, you need to be able to lose 2 drives and not have a problem. So the permutation algorithm is essentially going through making sure the permutations do not destroy the redundancy, and at the same time give you as random a layout as possible for your data.
All right. Jan has 2 more questions, but I'm going to jump around someone else for now so that we can get everybody a chance. In practice, how has dRAID affected compression? That is, how much of the compression gains are lost in padding in your large block workload? So in general, I haven't seen a huge impact of the compression impacting throughput. I mean, the large block, if you're compressing your large data down to nothing, or to a very small block, of course, that's going to change the dynamics of the situation. Your logical throughput is going to remain very, very good. Your actual throughput, because you're doing a lot of smaller IOs, may drop, but that's not really an issue. I think, what you tend to see with when you start layering on compression on top of a dRAID is that the dRAID, the compression is obviously going to consume
processor to do that work, and that may end up slowing down your throughput because you're spending now a lot of time doing the compression work itself. But I don't think it materially impacts your layout beyond the fact that you know, as you're laying down smaller blocks, you may end up with some more padding than you would have had if you had laid down larger blocks. But since you're compressing, you're saving, so it doesn't seem like a problem to me.
Can I give an example out?
Yep.
So, like if you're using the default of 8 wide, like an 8 wide group, right? Then and using 4K disks, then that means that, you know, your allocation unit is 32K.
Yep.
So if you're taking like a 128K block and you're compressing it down, then, you know, you're probably adding on average like 16K extra, which is like, what is that, like 15% or something more space. So, you know, maybe instead of 2-to-1, your ratio is like 1.7-to-1 or something.
Right, right. So you're, yeah, exactly. So you don't get as much compressibility as you'd otherwise get, but you're still getting compression, yeah, and you get that extra padding going in.
And then maybe you want to go to the question about small block sizes, because that kind of ties in to this as well. There's a question from Jan about, is there a script to calculate optimal dRAID layouts for small block sizes like 8K or 16K?
So there's no script for calculating optimal dRAID layouts. I think you know, you as a sysadmin could sit there and say, all right, if my workloads are going to be comprised of a lot of 8K IO, and so Matt actually raised this question to me earlier of, you know, what's the recommendation, for example, if you're creating zvols, and should you change maybe your default block size in that case? And as you just said, yeah, if you're using an 8 wide stripe and your average block size is 8K, but your minimum allocation is 32K, you're not going to be happy. So there's definitely a situation where you have to balance and say, all right, if given a average block size, I can't, you know, a very large stripe width is not going to be a win for me. And so you need to account for your minimum allocation size in your calculation. So your minimum allocation size is going to be, you know, your stripe width times your sector size. And that's what you need to base your own calculations in terms of how do I lay out this dRAID.
Yeah, so you don't really need a script because it's so simple. Like it's a lot simpler than RAID-Z actually. So like if you're using record size 16K, you're not using compression, you're using 4K sector disks, then, you know, you have four sectors per block. So you want to use a dRAID that's group size 4 or a factor of 4. So basically 4 or 2 will lead to no additional padding there.
Right.
But you know, you might want to use compression.
Yes,
because database files compress really well.
Yeah, exactly. And so, yeah, basically have to just, yeah, it's a calculation of what is your average allocation size you think you're going to be, and then you can factor that into saying, okay, here's a group width that makes sense. You know, the thing is, people want everything. Of course, you want to be able to say, all right, I want a you know, 8 wide, 16 wide stripe because that's so much more efficient with my space. But if you're doing a lot of small IOs, you've lost all that gain. So,
all right, Matt.
Do we need to skip out for the? Should we call it and let folks go to lunch? Is that what you're going to suggest?
No, I want to know, because like this is kind of the last presentation. There is quite a lot of questions, so maybe we keep it going.
Yeah, since there's so many questions, I would say why don't we keep it going here, and if folks need to drop off for lunch, then go ahead, or if folks want to go to the breakout rooms, then you can go ahead. But it seems like there's a lot of interest on this, so why don't we keep going here for those who want to continue.
All right, so I will continue the questions in a chronological order. So from Jan, could RAID-Z expansion work on dRAID?
So that's exactly, so RAID-Z expansion, so Matt, so I assume people are familiar, or Matt, are people familiar with your RAID-Z expansion work? That is what we are essentially leveraging the same ideas from that for the dRAID expansion concept. So it's a little more involved, a little more complicated, a little more space needs to be preserved, we believe. I mean, we sort of thrown around some ideas. I think I have a sort of preliminary design in my head around it, but it's essentially the same, conceptually very similar idea.
Yeah, we come to the hackathon tomorrow because I think Mark is going to be hopefully digging into this some more. And I think that it is conceptually simpler in a lot of ways than RAID-Z expansion because, like with dRAID, you know the widths of all of the like data to parity stuff.
Yeah, yes, true. That's true.
And when you're moving stuff around, like dRAID already has the concept of like, this is the logical width of my thing. And then like you have more drives than that, right? Like you have your group width is 8, but you have like, 37 drives. And so I'm like taking those 8 and kind of like,
that's right.
sorting them into the slice. So when you do dRAID expansion, you're just like reshuffling that, but the groups are all going to stay the same.
Right, exactly. And that's key, right? Your group size doesn't change, which in RAID-Z expansion, your group size changes suddenly, and that causes hell. So yeah, agreed.
Okay, next question. Another one from Jan. How much does dRAID improve read latency during resilver or rebuild? And read latency peaks, more precisely.
So read latency of other processes is what he's interested in there, I think.
Yeah, I think compared to like RAID-Z.
Yeah, I think that that is still from the work that we've done measuring it. I think there's still, I don't know, obviously you can tune your resilver rates to try to compensate for what you want in terms of other workload latencies. But we have not done enough work there to be able to tell you definitively, here are the right settings for this much impact or that little impact on your workloads during resilver process. In general, you're going to see that your reads are, you're competing your reads across all the spindles, but you are using all the spindles all the time. So it's going to be an even match. And so it's just a matter of saying, all right, how do you want to balance your resilver reads versus any other reads that might be ongoing? Does that make sense?
Yeah, makes sense to me. A question from Ryan, since this is built on the existing RAID-Z code, does that mean it already has vectorized math operation?
Like the
vectorized math
AVX and stuff like that. Yeah, I'm pretty sure it does.
Yeah.
It's just, it's literally calling into the RAID-Z code, and then that's going to use the, optimized RAID-Z,
Correct.
instructions.
Correct. Yes, exactly.
All right, next question, anonymous attendee. How does drive replacement work with dRAID since you're not working with physical drive representations?
So, obviously, you still have physical drive issues here. So when you do when you have an issue with a drive failure, it's a physical drive failure. You don't logically lose drives. You physically lose drives, and so. The difference is that in dRAID, in RAID-Z, when you physically lose a drive, you say, all right, I lost this drive, which is this column, out of this particular RAID-Z group. In dRAID, I've lost this physical drive, which is impacting all of my groups evenly, pretty much, because you have a random data distribution. And so when I replace it with a new physical drive, I'm going to pull from all of the other groups, all the groups, to rebuild onto that drive. And if you have a distributed hot spare, you're going to actually rebuild onto the distributed hot spare. And then when you actually physically replace the drive, you're going to resilver from that distributed hot spare onto the replacement drive. And so you're, again, leveraging all of your distributed spare data to rebuild, to recover a physical drive again.
All right. Question from James. I think I understand replacement in terms of return pool to redundancy via distributed spare. But what are the replacement in terms of physically replacing a failed drive? how is a new distributed spare added back to the pool?
And I hope I just answered that question from the last question, which is once you've rebuilt onto your distributed spare space, when you replace the physical drive, resilvers basically from the distributed spare space back onto the new physical drive.
Right. Question from, sorry for your name, Jim Leon. Is the cluster store product a Cray going to be on ZFS? The Cray distributed storage you mentioned?
So yes, the product, the base product at Cray, now HPE, is the cluster storage product, and that is being in its next generation version will have the option of using ZFS as its underlying storage.
Exciting. All right. Question from Ted. Along with expansion, could you do dRAID reduction as long as you don't go below the group size?
So reduction is, I think, conceivable, but complicated. With expansion, you have the advantage that you're growing your space, and so as you're rewriting, you always have space available to write it in your new version of the data once you've sort of copied aside some small amount of it. With reduction, assuming you have, you could do the calculation or have enough space around to somehow reduce this pool and remove a drive, but it seems quite complicated to me to figure out how to do that sort of on the fly.
Yeah, I think that you'd essentially have to have the no allocations past the point that you're removing, so that you could just kind of trim off the end.
Yeah.
Which means you have to change either the way the allocator works, or you'd have to add it as add the devices as not their full sizes or something like that, so that you preserve the end of it not being allocated, just in case you want to remove a disk.
Right. Which
you're probably not planning ahead if you're when you want to remove the drive.
Exactly. Removing a disk is usually like, oops, I messed up.
All right. Question from Stuart. Can you talk about how resilver load affects performance? Don't you find you need to throttle resilver? Yeah,
so that's related to an earlier question, and yeah, there's definitely going to be trade-offs. I mean, and this situation, whenever you talk about resilver performance and its impact on ongoing workload, every customer, everybody has a different feeling about it. Typically, it's like some people are like, I don't care. I want to restore my my full redundancy as quickly as possible. I don't care what impact I have on my ongoing workloads. Others will say, no, I'm willing to take a risk, let it go a little longer, and but just don't have too much impact on my ongoing workload, because that's more critical to me, for example. So I think there is some tunables in that space. You can tweak it and play with it, and as I answered earlier, I don't know that we have the complete answer as to here is exactly the right tunings for this amount of impact versus that amount of impact. And I think there is actually space in the project for some follow-on work where we may end up tweaking or adding some extra tunables to allow more fine-grained control. I don't know, but until we have more experience with it, I can't. That's the best I can give an answer to.
All right, thank you. I think last two questions, then the remaining, if there is any more, can be done at the breakout sessions.
Okay.
So one from Becky, do you recommend or not using dRAID with NVMe drives?
Absolutely recommend it. So this is an example where we do use dRAID on NVMe at HPE on our product. When we add in the direct I/O work, which is forthcoming also as a new feature in ZFS, actual implementation of dRAID, of direct I/O, that is, we see some very good performance numbers off of NVMe, and it can benefit. I mean, it's not as critical in terms of rebuilds because NVMe is so much faster, but it still works well, and it's a good choice.
All right. Last question from Jan. Does a dRAID rebuild trigger a resilver?
Yes. So any sequential, no, sorry, dRAID rebuild trigger resilver. Back to our sequential construction, sequential resilver discussion earlier. A dRAID rebuild is just a sequential resilver. And after sequential resilver, we always trigger a scrub activity. And so that happens as a scrub, not a resilver. But yes, I guess I think that the answer is looking for is yes there.
Okay, thank you. And looks like Becky wants to squeeze one last follow-up. So this is going to be the last one for real. Does it require a particular type of NVMe?
So, our experiments to date have been on some pretty high-end NVMe drives, 3.8 terabyte drives that are capable of doing, on the order of 4 gig a second sort of transfer rates. Those work well for us, but I don't think it necessarily depends on a particular NVMe drive type. I mean, obviously you want to, calculate in or factor in, drive writes per day calculations, that kind of stuff. But, dRAID isn't necessarily any different in terms of its I/O use patterns to any other ZFS configuration that you might choose. I don't think there's a particular NVMe type that would make sense, more or less sense